Saxon Algebra 1, Lesson 33. We have a two-parter today, both algebra. The first part is kind of the smaller piece, and it's about prime factor trees. I have to set the stage for you, though. It is raining outside like it can only rain in the Pacific Northwest. You know what I mean? It's not raining hard, but it's raining misty and chunky and thick. The air is just like full of tiny drops. The only way it could be more Pacific Northwesty is if it was like raining slugs. You know what I'm saying? So it's a little gloomy. I hope the light's okay. But I just want to set the stage. So just curl up, get a blanket, and we will do this. Before we talk about prime factor trees exactly, I want to remind you of what a prime number is. And the best way to remind you of what a prime number is to remind you of what a prime number isn't. The name for that kind of number is called a composite number. And a composite number is one that we can find two other numbers that will multiply to equal it. So for example, 6 is a composite number because we can find, oh, that's equal to 3 times 2. 81 is a composite number because that's 9 times 9. And let's do one more example. 15 is a composite number because it's 3 times 5. So basically, you know all those multiplication facts that you've been working on memorizing for the last, I don't know, however many years, 8 years, whatever. All of those multiplication facts that you know are probably composite numbers because two things equal them, right? All those products are equal to factor times factor. That's a composite number. Now, in these cases, we could also multiply the number times 1, right? That's always a multiplication fact that would work. But composite numbers are numbers that can be found using multiplication of two numbers that aren't that number and 1, okay? So they have other more interesting factors. A prime number is a number that does not have interesting factors. A great prime number is 17. The only way to get 17 is to multiply 7. Oops, what happened there? 17 times 1. Okay, 23 is another prime number. The only way to get it is 23 times 1. And let's see, let's think of one more. What about 37? I'm pretty sure is a prime. And the only way to get that one is 1 times 37. I'm writing these in different order, but it doesn't matter. Prime numbers do not have interesting factors, okay? That's what makes them. And by interesting, I'm saying these are not interesting. The only way to get a prime number by multiplying is to multiply the number itself times 1. That makes it prime. They have no interesting factors, and they're just sad and lonely. Okay? Now, so that means any number we're given that is a composite number, we can break down into a series of prime numbers. 3 and 2 are both prime numbers, aren't they? So we have broken this composite number down into 2 primes. This is also a composite number broken down into 2 primes. But sometimes we'll have a number like 81 where we can break it down into 2 factors, but these aren't prime numbers either because both of these represent 3 times 3. So those are interesting factors too, right? So sometimes it takes multiple steps to break a number, a composite number down to its primes. But that is a very useful tool that we're going to use all kinds of times in your future algebra. It makes so many calculations so much easier if we can mentally break a number down into its primes. So we're going to practice that. If you can't do it in your head now, then you're a normal human being. We want to get so familiar with it and fluid with it that you can do it in your head as much as possible. That will save you a lot of time in the future. So we're going to practice. Here comes the first example. We just have 2 examples in this section. And John asks us to express 80 as a product of prime factors. So he's saying take 80, break it down and keep breaking it down until you get all the way to prime numbers, all right? So the way we start is we draw this little thing. This is the first branch in the tree. And we think of any two numbers that multiply to 80. The first ones that pop into my head are 8 and 10. But the first ones that pop into your head might be 40 times 2, for example, right? Or we could do 5 times, I guess it would be 16. Whatever pops into your head, there's no right or wrong. We will all get the same answer in the end. I look at these two numbers, these are the ones I chose, and I ask myself, is either one of these prime? And what I'm really asking is, can you think of any two interesting numbers, not 8 and 1, not 10 and 1, that's not interesting. Can you think of any interesting numbers that multiply to this number? And I think, yeah, 4 times 2. Okay, now we go further down the tree. Can we think of anything interesting that multiplies to 4? Yes, that would be 2 and 2. Can we think of anything that multiplies to 2? No, that we've reached the end, right? That's just 2 times 1. So we circle it because that's a prime factor. Here's another 2, that's a prime factor. Here's another 2 that we dead-ended up here. That's another prime factor. When you get to a prime number, circle it. What about 10? Can we break that down? Yes, we can break that down into 5 and 2, and these are both prime numbers. So now we can say that 80 equals, and we just write it all out. Let's see, I usually like to put them in order from smallest to biggest. So I know 2 is first, 1, 2, 3, 4 2s, and a 5. That is the way we express the number 80 as a product of prime factors. We calculated it here and we summarize it thusly. Example 33.2. Express 147 as a product of prime factors. Now, this one's a little trickier because I don't know about you, but this was a lot easier to think of two numbers that multiplied to it, right? 8 times 10, that was pretty easy. But I don't know right off the bat how to find two numbers that multiply to 47. They don't jump magically into my head. So what we're going to do is we're going to remember the different rules we have for divisibility. So for example, if it's an even number, then it's divisible by 2. If it ends in 0, then it's divisible by 10. If it ends in 5 or 0, it's divisible by 5. If the digits add to 3, then it's divisible by 3. And that's the weirdest rule, right? These are they're called rules for divisibility. They don't give us every situation because, like, what if a number is divisible by 7 or 13? Those are harder to see, but these are some great rules that help us with a lot of situations where we're trying to figure out what divides into a number, which is what we're doing. So let's add up. Let's give this the test for 3s. 1 plus 4 is 5. 5 plus 7 is 12. I'm adding the digits and completely ignoring their place value. I'm just adding them up and I get 12. I ask myself, is 12 divisible by 3? Yes, it is. So that means 147 is divisible by 3. I never would have guessed. So let's divide 147 by 3 and see what we get. 3 into 14, let's see, 3 times 4 is 12. So I'll use that and I subtract and I get 27. Okay, 3 into 27 is 9 times. Okay, so what, and that comes out even. So what we have found is that 3 times 49 equals 147. So let's do that. 3 times 49. 3 is a prime number. Oh, that's nice. 49 looks like it could be, but if you remember your multiplication facts, which is really what this is all about, we see that that's 7 times 7, and 7 is also a prime number. All right, if you're not sure if a number is prime, because really what we're doing is leaning into our multiplication facts. So if you feel a little shaky on your multiplication facts, this can be a little bit of a workout for you. It can be a little bit confusing. You can always just Google, is 7 a prime number? Or you can Google list of prime numbers and just look and see if 7's on it. That's probably the easiest way, so you don't have to Google every time you're figuring it out. Or better yet, you can copy for yourself into your notes a list of the prime numbers up till 50. That would be a really great idea if you feel uncertain of your prime numbers situation. That will make these problems a lot easier. 7 is prime. So now I can write, just like I did here, I'm going to write 147 equals, and it's 3 times 7 times 7. Okay, so we did the prime factors of 147 as well, and that's correct. All right, we're going to continue to work on these. I'm going to talk about doing it more as I'm solving certain kinds of problems, so that your brain will get into the flow of this. Because like I said, we're going to use it a ton. Okay, next topic. You know these word problems that we've been doing, we're going to expand on them in kind of a kooky way. Up until now, we have been comparing, let's see, these are, I'm going to give this the name John gave it. It sounds cumbersome, but it will make sense later. In the word problems we have been doing up till now, John has been describing one wacky thing, right? 5 times the sum of 17 and a number is or equals that number decreased by 46, something like that, right? And so the words we use here are is or equals, and the sign we put here is an equal sign. And this is a quantity, and this is another quantity. Those vary, right? John mixes it up and gives us different long, wordy explanations, and we fill in the symbols accordingly, right? So they are the same quantity. They're equal to each other, and so we've been able to connect them with an equal sign. Well, that's about to change. Now he's going to give us situations where he gives us a quantity, right? 3 times the opposite of a number is greater than another quantity, or he'll say blah, 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 is less than. Oops. That should come at the end. Blah, 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 blah. When he gives us numbers like this, he will always tell us a certain number, how much less than or greater than. There will always be a number before the words greater than or less than. And I call that the adjusting number. The way we will work these problems, and they're tricky and they're hard, is first we will write an inequality. And then we will use the adjusting number to make it balance, to make it equal. Okay, write that down. And then I'll show you and you'll be like, oh, okay. It will make sense very soon. And we will do the first example. The examples always the explanations are kind of hard to wrap your brain around. I know. It's hard to explain math in words. It's easier just to do it. It makes more sense. 33.3. Now, once again, like I've done in previous lessons, I'm going to write down the problem so that we can talk about it as we go. You don't necessarily need to do this in your homework, but if you get stuck by these, I highly recommend doing it. Twice a number okay, this is exactly word for word what John has. Twice a number is 42 less than minus 102. And then he says, find the number. I'm not going to write that. Okay, so our eyes go first to this. And we realize this is the pattern where we're going to have quantity and then less than and then another quantity. All right? We're going to write the inequality first and then we'll figure out how to adjust it. So this is step one, write the inequality. Twice a number, I'll just write it right in here. Twice a number this is the adjusting number. It's the number that comes before the greater than or less than. So we're going to leave that out for now. We're going to use that in step two. Twice a number is less than minus 102. Okay? What we have written here is an inequality. It's less than. So now, in the second step, we will fix this using the adjusting number. Now, in order to figure out how to use the adjusting number, you have to think logically. This is less than this. Which of those numbers then is bigger? This is the bigger number, right? Because it's the larger one. This has to be the smaller one. We always adjust on this side. So the way I'm going to use this balancing number is I'm going to subtract it from this side. I'm going to write 2n equals minus 102 minus 42. There's my adjusting number. I subtract to make the greater side smaller, right? This is the greater side. I can tell by looking at this. It says 2n is less than 102. That means 102 is the greater side. So I have to make this side smaller by the adjusting number in order to create a true equation. Beautiful. That's it. The adjusting number is always right in front of the greater than or less than words. All right? So it's easy to find. All right, from here on out, it's pretty straightforward. We just solve this. So I'm going to do the next step. It would be 2n equals minus what, 144. And then we divide both sides by 2 to isolate the n. And we get n equals minus what, 72, right? And that's the correct answer. Okay? So we find the words that describe the inequality. We write it as an inequality. We ignore this adjusting number in the first round because that's right in front of these words. We know where to find it. Now we use that to logic our way. And if this one's less than, then that means this is greater than. That means we need to subtract in order to get them to balance. Now we'll do one that works the other way. And hopefully it will all start to fall into place for you. Then I'm going to do the same thing. I'm going to write out the actual problem so that we can see how all the words work. 5 times a number is 72 greater than the opposite of the number. Okay, we look for the words greater than or less than. There they are. We know that that means we're going to have something is greater than something in our first round. We see there's our adjusting number. We'll hang on to that. We won't put it in on the first step. We'll use this on the second step to balance. Okay, 5 times a number is greater than, right? I ignore that number, is greater than the opposite of the number. There, I've written an inequality to get me started. Now I used the adjusting number to balance. Before I start writing, I think, using just logic, okay, 5n is greater than minus n. We always adjust the second half of the inequality, the future equation. If this one is larger, then this one is smaller. That means I need to add the adjusting number. Equals minus n plus 72. Okay, so here's a little rule we can work with. If it's less than, then we subtract the adjusting number on the right side of the equation. If it's the other way, if it's greater than, then we add, oh, I forgot the T. The adjusting number on the right. Oh, I'm having a hard time getting my words out, aren't I? All right, so this is the rule that I am generalizing. You really don't have to memorize this directly because you can just use common sense. If this is greater than this, and we're adjusting on this side, then we have to add over here. Okay, now we have a nice equation that we can easily add. 6n equals 72, divide both sides by 6, and we get n equals 12. Is that the right answer? Yay, it is. All right, so this rule can help you test your logic, but just use logic to say which side is already bigger than the other and how can I use the adjusting number on the right side to make it balanced. Some teachers will give you the choice of adjusting the left or the right. I think that's needlessly confusing. Always adjust on the right side. There's more room to write anyway. And that way we can make a general rule about it. Okay, one more of these. 2 more. Example 33.5. If the sum of twice a number and minus 14 Okay, that's problem 33.5. I'll give you a second to finish writing. Okay, that was a lot. That was a lot to write. Look, it took up over half my page because I write so big. I don't expect you to do that for every problem in your homework. It was one thing for those first two problems because they were a lot shorter. But now we're writing a novel, and that's ridiculous. So here's the way I want you to approach these so you don't have to copy them. First, look for the inequality words, greater than or less than. Underline them, circle the number that comes before them. On your paper, write down adjusting. You can do that, you know how hashtag means number. Write adjusting number equals 12, and then write this. Something is greater than something else, okay? So you can do just this much. Now go back and look at these phrases and turn each side into an algebraic expression. The sum of twice a number and 14, okay, that's 2n plus 14. If the sum of twice a number plus 14 is multiplied by 2, the result is greater than the opposite of the number. Make sense? And sometimes I have to go through and read these again and just think carefully. The sum of twice a number and 14, okay, sum means we're adding. And then we multiply the sum by 2, okay? So I have to put parentheses around to show I mean the whole thing. Times 2, the result is greater than the opposite of the number. Okay, that's pretty easy. Now, this is the bigger side, this is the smaller side. That means I need to add 12 to make them equal. And now I can just change that. This is the way you can do it in your homework to minimize the amount of work that you're doing. I still want you to identify your adjusting number right off the bat and write the inequality. Then you can just adjust and change to equal sign in one fell swoop so that you don't have to keep copying everything. Now we'll distribute. 4n plus 28 equals minus n plus 12. This is a minus though. No, wait. Yes. Here's what I did wrong. I copied that wrong. That should be minus 14. The sum of twice a number and minus 14, this should be a minus. And so this should be a minus. All right? I just copied right there. I forgot. I dropped it when I copied it right there. So now we'll just put it back in. Everything else is fine. The way we set this up doesn't change at all. Okay, so now let's do this. Let's add 28 and swim that over here. And then let's swim the n fishy over this way. So plain numbers on this side. On the right, now we have 5n equals 40. Divide both sides by 5. And we get n equals 8. The algebra of these is straightforward. You shouldn't have any problems with that. What we're really focusing on here is how to write out these problems. And this is what John said. It's statements about two unequal quantities, right? Because we're saying they're either greater than or less than each other. So we have to have a new way of processing that. Okay, one more, and we'll do it the homework way. No, I want to write it out. You don't have to, but I want to. It's too hard for me to show you what I'm talking about unless I write it out. But you don't have to in your homework. Okay, I'll give you a second to finish writing. I want you to write this out, but again, you don't have to do it in your homework. Let me just make sure I didn't drop any minus signs this time. Okay. Good. We look for the less than or greater than words, and we look for the adjusting number that come right before it. Adjusting number equals 21, and it's a less than, so we write something is less than something else. All right, there's the inequality. 5 times a number is, and we just ignore the adjusting number for now, less than, yes, twice the opposite of the number. Twice the opposite of the number. And just for clarification, I'm going to write this again. You wouldn't have to do this in your homework. This is correct, but it looks a little unfamiliar. So I write it that way because it matches to the words, and then I realize, oh, I can write that a better way. And so I fix it and write it this way next. Okay, now we have acute inequality. We're ready to do our adjusting. I can see that because this sign tells me that this side is smaller, this side is larger, so I know I need to subtract the 21 from this side in order to get them to balance. All right, and now that I can do this, I just write it right over the top. Okay, let's swim the 2n over here to his fellow n fishy. And I get 7n equals minus 21. Divide both sides by 7, and I get n equals minus 3. And that's correct. We're going to be doing these for a good long while. They are tricky. Use these tools that I've given you as to how to identify the important parts of your problem and write first the inequality and then the correct equation, all right? John does not use these same rules. I've developed these over time to help make these easier because students oftentimes really struggle with and hate these problems because they're so confusing. But hopefully this will help you. Okay, that's the end of 33. Thank you. Goodbye.